In the second video, second day of 8.4, we're going to add something new, something called oblique asymptotes. So we've done vertical asymptotes, we've done horizontal asymptotes, we're now adding oblique asymptotes, and those are also known as slant asymptotes. You could throw that word in there as well. So if you hear me say slant asymptote or an oblique asymptote, it means the exact same thing. So you know horizontal asymptotes are obviously horizontal and vertical asymptotes are vertical. Slant asymptotes are, just like they sound, they're slanted, they're diagonal lines that the graph has as an asymptote. So still the same idea as any old asymptote. You get closer and closer to that line but don't actually touch or cross. But this time instead of being horizontal or vertical, it's a diagonal line. All right? So it's an asymptote that is diagonal rather than horizontal or vertical. So the way the book defines it, they say it's an asymptote that is neither horizontal nor vertical. Okay, and it's not horizontal or vertical because it's diagonal, which is really your last option for lines. All right, so we're going to walk through how you'd find a an oblique asymptote and when you would even know to look for it. So the only time that a function has an oblique asymptote is if the degree of the numerator is 1 more than the degree of the denominator. All right, so let's walk through that. So when does it have an oblique asymptote? If the degree of the numerator, which is a of x, is 1 more than, than the degree of b of x, which is the denominator. Okay, so like an x cubed over an x squared over an x, something like that. Okay, so that's what you're looking for there. And so what we do to find the oblique asymptote is you divide the numerator by the denominator. So the equation for the asymptote you take a of x and you divide it by b of x, but you don't include the remainder. So we get to recap some of our division skills, maybe a little synthetic division perhaps. So this is, seems really weird because we haven't actually done any examples. I've just been giving you all of this kind of conceptual stuff, which like I said, it seems bizarre when you haven't actually seen an example. So let's look at example 3. We've got 2 there where you can see in part A, x squared is 1 more than x. Down here, x cubed is 1 more than x squared. So these are going to have slant asymptotes. We're going to graph them. We have the same 3 steps as we had before. So step 1 is still to find the zeros. So I'm still just going to write 1, 2, and 3. So step 1 is still to find the zeros. So we take the numerator and we set it equal to 0. And so the only one you get from that is just 0. Okay, so let's start our graph over here. So 0 right at the origin there. Step 2 is we want to find all of our asymptotes. Okay, so for a vertical asymptote, we set the denominator equal to 0, and so we come up with x equals 2. So let's graph that one in there. So 1, 2. Let's graph in our vertical asymptote. Horizontal asymptotes, there is not one because the numerator has a larger degree. So there's no horizontal asymptote, but because the numerator's degree is exactly 1 more, we know we have an oblique asymptote. All right, so let's worry about finding that. So finding the oblique asymptote, we're going to set up a little bit of long division. Oh, it's good stuff, guys. You're going to love it. All right, so for the oblique asymptote, we are going to take x squared, and we're going to divide it by x minus 2. Okay, kind of recap some of this long division stuff. So remember, when you're doing the long division, we really only care about the x. The negative 2 just kind of follows along. And so we've got x squared divided by x. Remember, we're basically trying to figure out how many times does x go into x squared, or what do you have to multiply x by in order to get x squared, and that would be x. So I put an x right here, and then I take x and I multiply it by x minus 2, and then I subtract. So x times x is x squared. X times negative 2 is negative 2x. I'm going to subtract. So these will cancel. And then I have nothing here. So 0 minus negative 2x leaves me with a 2x. Then I only have to do this one more time. How many times is x going to 2x? AKA, what do I multiply x by to get 2x? And that would be a positive 2. So then I multiply 2 back by the x minus 2, and I subtract. 2 times x is 2x. 2 times negative 2 is a negative 4. Okay, so these cancel, and then I have nothing minus a negative 4. So my remainder is 4, but the rule says I don't use my remainder anyway. So my oblique asymptote is the line y equals x plus 2. Okay, so let's get that line on our graph. So a little reminder on how to graph linear functions is we start with our y-intercept, which it says is at 2. So we've got a y-intercept here, and then this is technically a 1x, so I have a slope of 1. So from here, I can go up 1 to the right 1, or I can go down 1 and to the left 1. All right, so follow that diagonal line. Okay, so it looks like that. So here's my vertical asymptote, here's my slant asymptote. That's what we've got so far. Okay, so now when we're filling in some of the blank spots here, basically what happens is that I still get two pieces. I'm going to have a piece that goes in here, and I'm going to have a piece that goes in here. So just so you can see that other piece, I'm going to extend these lines just a little bit. Okay, so our line is going to look something like this. We're going to curve along this asymptote, go through this point, turn around and go back this way. And then here it's going to go something like this. Okay, it's basically like you're using those dotted lines as your guide for how to graph your function. Okay, so that one looks something like that. Maybe I start shrinking these down a little bit. All right, next one. First step, we are going to set our numerator equal to 0 to get our x-intercepts. Okay, so I can add 1 to both sides, and I get x cubed equals 1, and then take the cube root of both sides, and I just get 1. Okay, so 1 right there. Next, I look for my asymptotes. So for my vertical asymptote, I set x squared minus 4 equal to 0. I can add 4 to both sides, and I get x squared equals 4. Be very, very careful with this next step. When you square root both sides, we actually end up with a plus or minus 2. So let's start there. So here's positive 2, here's negative 2. So we've got 2 vertical asymptotes to sketch in this time. Okay, so they look like that. We have no horizontal asymptote because the numerator's degree is larger, so we're going to work on finding our oblique asymptote. Okay, so for our oblique asymptote, we are going to take the x cubed minus 1 and divide it by the x squared minus 4. So we are focused only on this piece right here. We want to know how many times does x squared go into x cubed, and that would be x times, because x times x squared gives me x cubed. Then I multiply and subtract. So x times x squared gives me x cubed, and x times negative 4x, times negative 4 gives me negative 4x. So this cancels. Now be very careful. I have a negative 1 which does not combine with this 4x. So I have minus negative 4x, which is 4x, and then I have a negative 1. We probably should have left some spaces here like we used to, but we'll be fine. So now how many times does x squared go into 4x? Well, it doesn't. So this would be my remainder. So we don't need to worry about the remainder. So my oblique asymptote is the line y equals x. So let's get to work on graphing that. All right, so just y equals x is a very, very simple linear function. It goes right through the origin. It's got a slope of 1, so I can go up 1 to the right 1. I can also go down 1 to the left 1. Sketch that diagonal line in here. It's basically just like the most generic diagonal line that you can do. Goes like at a 45-degree angle straight through the origin. All right, so it looks something like that. So this one, this is a very bizarre graph that we've got here. So with this one, we're definitely going to want to come up with some more points. All right, so we know exactly what this one is going to look like. So let's plug some points into our calculator and come up with a table. Okay, so let's plug in 0 and see what we get. Let's plug in a -1. We already know where we are at 1. And let's plug in some other points over here. Let's plug in like 3, 4. And let's plug in some points over here, -3, -4. Okay, hopefully that'll give us a good picture. So we are going to define another function. And so let's plug that right into our calculator. So do menu again, oops, there's a weird glare, sorry. Menu again, actions, and define. We'll plug in our function, f of x equals another fraction, x cubed minus 1, and then in the denominator, x squared minus 4. So this one we got to get a good picture here. Okay, so it's defined. Let's plug in these values. So f of 0 is 1/4, or 0.25. F of -1 is 2/3, or 0.67. F of 3, whoops, not negative. F of 3 is 5.2. F of 4, 5.25. Okay, very close, so we'll see what that ends up looking like. And then off to the other side, f of -3 is -5.6. And f of -4, so this might be enough, we'll find out, -5.42. Okay, so let's plug some sample values in here, see what we got. So at 0, we're at 0.25, so just right above that line. -1 is at 0.67. Okay, and then 3, so we're going to go right here. They're at 5.2, so here's 1, 2, 3, 4, 5. So right about there, so kind of right in the middle. That part's kind of expected. At 4, we've got 5.25, so just a little bit higher, maybe right there. -3 is at -5.6. So here's -3, and then we've got -2, 3, 4, 5. So right about there, again, kind of as expected, right in the middle of those two dotted lines. And then -4 is at -5.42. All right, so just a little bit higher. Okay, so they're they're basically right on top of each other, like right about there. Okay, so these ones are pretty easy. This just kind of goes like this. You know, just really follows those pink lines. This one's going to do the same thing. Okay, so those two pieces make a lot of sense. Now this in here, this is what I've said about making the tables. I can't give you a predetermined, like, hey, this is going to be the perfect table to make, because you really just need to explore. So we need to see what on earth is happening right about here. So somewhere in between 1 and 2. So let's try 1.5. Okay, so about -1.36. So that would be like right here. Okay, and let's check the other side. F of -1.5. Okay, and that's about 2.5, so that's actually pretty high. So right about there. Okay, so here's what this piece does. Is it actually is going to drag along here and then do that. All right, so we've got one exception here is that you can actually cross through a line as long as kind of the end behavior drags along these lines. So it's this part that's important and this part that's important. Every once in a while you will cross through just at one point, but the important part, like I said, is that you're getting closer and closer to that line as you head off in one direction. Okay, let's look at the next idea. This last idea of 8.4 is that we could have this thing called a point discontinuity, which is similar to a vertical asymptote, but it's one very specific situation. Okay, so let's say point discontinuity is going to look something like this. First of all, it looks like a hole in the graph. Okay, so it's a hole in the graph. So here's the situation. We've got f of x. I'm going to set this up. So just to write our generic form one more time. So a of x, b of x. Here's when you have a hole. Okay, so if x minus c, so some generic factor, x plus 1 or x minus 2 or something, is a factor of both a and b. Okay, so if x equals c is a factor of both a and b, then there is a hole at x equals c. Okay, so we're going to graph that. All right, so let's take a look at that first one, example 4. We're going to have some examples that have point discontinuities. So this guy right here, and we're going to factor. All right, that's going to be our first step in some of these. So here, if we factor this down, we start with x and x. And then over the x plus 5, doesn't need to factor. So the reason you'll know which ones these ones are, because remember in the book it kind of matches with the right examples. Like these ones in the book will match up with example 4. You don't have to get in the habit of factoring every single one. All right, so here we want to know what's going to multiply to negative 5 and add to positive 4, and that would be an x plus 5, x minus 1. So let's go back to this point discontinuity definition. It says that if x minus c is a factor of both a and x, then there's a hole there. Okay? So what happens, we factor this down, you notice you've got a common factor, x plus 5 and x plus 5. So essentially what's going to happen is that we're going to cancel these out, but we're going to list it as a discontinuity. Okay, so x can't equal negative 5. So here's the difference. In the previous problems, anytime the denominator was 0, we had a vertical asymptote. This is the one exception. In this case where I had a factor in the denominator, but I also had the exact same factor in the numerator, it ends up being a hole rather than a vertical asymptote. So there are two different types of discontinuity. All right? So this, when I go to graph it, it actually looks just like this, except there's a hole where the negative 5 should be. Okay? So let's see what would happen if we did plug in the negative 5. Okay, so plug in x equals negative 5 into this part that I just boxed in, and we have negative 5 minus 1, which is negative 6. All right, so what this has is a hole at negative 5, negative 6, but other than that, it looks just like this graph right here. Okay, so let's sketch it. Okay, so the graph x minus 1, it has a y-intercept of negative 1, and then it's got a slope of 1. So we're going to go, up 1, over 1. We could go down 1 and to the left 1 like that. And I'm going to plot a hole. I would have a hole at negative 5. So here's negative 1, 2, 3, 4, 5. Negative 6. This is negative 1, 2, 3, 4, 5, 6. Okay, so right here. And here's what we do is you literally just do that. And then sketch in the line. Okay, and kind of make it go a little bit in the other direction. So it looks like that. It looks exactly like this line would look, except that there's going to be a hole when x is negative 5. Because if you look at the original graph, I'm not allowed to plug the negative 5 in. So these graphs are kind of weird. Let's look at one more. So we're going to start by factoring this one as well. This one in the numerator, we've got to factor by groupings. Let's remind ourselves of that. So this I can factor out an x squared. And then I have an x plus 2 left over. And then here I can factor out a negative 9, and then I'll have an x plus 2 left over. And in the denominator, I have an x squared minus 9. Okay, so let's keep factoring this. So here I can factor out the common x plus 2, and then I have x squared minus 9. And then in the denominator, I have an x squared minus 9. So like I said, up in the one above, I can cancel these out. However, I have to state that x squared can't equal negative 9, which means, since this is the difference of squares, x can't equal plus or minus 3. So my graph is going to look just like this graph, except I'm going to have a hole at positive 3 and negative 3. Okay, so let's plug them in. Where are my holes going to be? Okay, so if I try to plug in positive 3, I'd have positive 3 plus 2, which is 5. And then if I try to plug in negative 3, I have negative 3 plus 2, which is negative 1. So I'm going to have holes at those 2 points, but other than that, it's going to look just like this graph. Okay, so let's start. We've got a y-intercept of 2. I have a hole at 3, 5. Okay, so we literally are just going to draw a hole like that, okay? And then negative 3, negative 1. Like that. Okay, so we draw our linear function. Go right through the hole. Or I guess go around the hole, sort of. Go right through that point, and your graph looks like that. So it looks just like a linear function, except I've got a couple holes. Okay, so that is the end of 8.4. So we've got lots and lots of graphing stuff that we've looked at.